Welcome to The Explainer. Today we're unpacking a genuinely wild proposal that aims to completely redefine how we detect the invisible. We are diving into an incredibly ambitious design document for an indigenous hybrid quantum radar system. Now, this isn't just some minor incremental upgrade to existing tech. It's a proposal that claims it can crack the ultimate defense problem, spotting low observable stealth targets using a massive leap in room temperature quantum physics. It's a dense, highly technical roadmap, but we're going to break the whole thing down together.
All right, here's our roadmap for today. We'll start with the core stealth radar problem, move into the promise of quantum radar, and then hit the real star of the show, the room temperature breakthrough. After that, we'll break down how the hybrid system actually works, how it plans to survive real-world naval challenges, and finally wrap up with its hyper-aggressive 24-month deployment plan.
Okay, part one, the stealth radar problem, and frankly, the hard limits of classical tech.
So, think about it. How do you detect a target that's practically invisible? Classical radar is basically just shouting into the dark and listening for an echo, right? It's all about reflected energy. But modern stealth aircraft are literally built to absorb or deflect that energy, while active electronic jammers are just screaming over whatever tiny echo might actually bounce back to you. And because of that, even our most powerful classical naval radars are hitting a physics wall. Against heavily jammed or stealthy targets out in a complex maritime environment, the return signal just gets completely buried under the classical noise floor. It's like trying to hear a whisper during a hurricane. Classical tech just can't filter the signal from the noise effectively anymore.
Which means we need a totally new way to see. Enter part two, quantum radar. Its massive promise and its equally massive cryogenic bottleneck. Now, quantum physics offers a pretty brilliant workaround here called quantum illumination. Instead of just waiting for a loud echo, the system creates a pair of entangled photons. Think of them as twins. You keep one twin, the idler, inside the radar, and you shoot the other one, the signal, out at the target. When that signal photon eventually bounces back, the system checks for a statistical correlation with its twin. Because they're entangled, the radar can mathematically prove that this specific tiny returning whisper belongs to its original shout. Boom, energy jamming and background noise instantly filtered out. But yeah, there's a huge catch. Right now, the global state-of-the-art for this tech requires dilution refrigerators running at 10 millikelvin. That is literally colder than deep space. These setups weigh 500 kilos, suck up 10 kilowatts of power, and are strictly confined to highly controlled labs. But out in the real world, the operational requirement is that this thing has to fit on a moving naval corvette or even a drone. You just can't strap a half-ton, ultra-sensitive deep freeze unit to a drone and expect it to fly.
And that is exactly what makes this document so fascinating. Part 3, the room temperature breakthrough, or how to ditch the dilution refrigerator.
This proposed hybrid quantum radar completely flips the script. The designers have laid out a method to generate these entangled photons at ambient temperatures. No crazy cryogenic schooling needed at all. And by making that shift, they're proposing dropping the weight from 500 kilograms down to just 40. The power drop drops to a mere 225 watts. That right there is the exact difference between a neat lab experiment and a lethal deployable weapons system. So how do they pull this off? It all comes down to a glowing little cube called a PPKTP crystal. The proposal uses a process called spontaneous parametric down conversion, or SPDC for short. They basically fire a 405 nanometer pump laser into this specialized crystal, and it splits that beam into 10 million entangled photon pairs every single second, all at room temperature. This tiny crystal is essentially the beating heart of the whole operation. Okay, so we have the crystal. How does that become a working radar? Let's get into part 4, how the system actually works, looking at its hybrid architecture.
This is where the hybrid part really shines. You've got the cutting-edge quantum world on one side, with the SPDC crystal spitting out photons, married to the classical world on the other. Because honestly, making entangled photons is just step one. You still have to process millions of them instantly to actually spot a target. So the proposal takes all that raw quantum data and slams it into a blistering fast classical FPGA microchip, basically a heavy-duty correlation engine built just to handle the data fire hose. The internal architecture here is wild. The system time tags every single photon at a picosecond resolution. Guys, that is 1/1,000,000th of a second. It buffers that incoming stream on the FPGA chip and then feeds it straight into an advanced AI fusion processor. This AI uses a convolutional and recurrent neural network to fuse the quantum correlation maps with classical radio frequency features. If we strip away the jargon, it's a 4-step pipeline. Step 1, detect the signal and idler photons. Step 2, buffer them incredibly fast on the FPGA. Step 3, run them through a coincidence matching engine to absolutely verify the entanglement. And step 4, let the AI spit out a target detection map. According to the blueprint, this entire end-to-end loop runs in under 100 milliseconds. That's real-time actionable targeting data right there. When you look at the comparison matrix, the goal is pretty obvious. Classical radar, it works at room temperature and you can deploy it, but stealth beats it. Cryogenic quantum radar, it beats stealth, but it's a massive, freezing lab princess. This proposed hybrid quantum radar claims it can check all 3 boxes at once: room temp, stealth busting, and naval deployable. The best of both worlds. But hey, checking boxes on a slide is one thing. Building hardware for the ocean is another. Part 5. Overcoming real-world challenges and moving from the lab to the sea. The designers know this is risky, and they've got specific mitigations planned out. Take entanglement fragility. Sea spray and atmosphere will absolutely chew up a quantum link. Their fix? Using AI fusion to mathematically claw back 6 to 12 decibels of signal gain from whatever tiny correlations actually survive the trip. Then there's the domain mismatch, the total headache of mixing gigahertz classical radar waves with terahertz optical quantum photons. They're bridging that gap with a highly specialized electro-optomechanical transducer. Add an active thermal feedback and waterproof IP67 enclosures to protect the optics, plus adaptive AI thresholds to filter out the false alarms while processing 10 million events a second. If they can actually pull those workarounds off, the end result is a ruggedized 40-kilogram box. They're taking a setup that used to fill an entire freezing laboratory and stuffing it into a highly deployable module. That is exactly why this is viewed as an absolute game changer for sovereign tech. It's light and power efficient enough to bolt onto a drone or a ship without needing a massive multi-million-dollar overhaul of the hull. So when is this supposed to happen? Let's hit our final section, Part 6, the road to deployment, featuring a frankly insane 24-month execution plan. The roadmap here is hyper-aggressive. Months 1 through 3, spin up a lab demonstrator to prove the room temp physics. By month 9, they aim to have an integrated prototype ready. Months 10 through 15 are dedicated to field testing and actually training their AI against live electronic jamming. And then, this is the crazy part, months 16 through 24 are slated for full naval integration. We're talking drone payload trials and actual deck mounting on a corvette. If you look at the proposed budget to fund this sprint, the biggest chunk, about 34%, goes straight to mechanical integration. Making it actually survive on a ship. But a huge portion of the rest is pure frontier science, 22% on photonics components and 16% on AI fusion and training. They aren't just building a sensor here. They're trying to build a completely new, intelligent defense ecosystem. I really want to linger on this number, 24 months, to go from blueprints to a technology readiness level 7 capability. In the defense world, where procurement usually drags out over decades, a 2-year timeline is an absolute speed run. We've looked at the physics, the hybrid tech, and that wild timeline. So I'll leave you with this. If this 40-kilogram box works exactly as proposed, if it successfully drags quantum radar out of the deep freeze lab and onto the high seas, how do the rules of naval warfare change when stealth practically disappears overnight? When the invisible is suddenly visible, the entire game resets. Thanks for joining me on this explainer, and I'll see you next time.